and welcome to Google Cloud Next 2026. Thank you all for coming in. I know it's late, and I know we have some competition with some other great sessions on similar topics at this time. Before we dive into the tech, we wanted to start with a quick GPU support group, just to see who is our audience here and what are the challenges we all are facing. So with a raise of the hand, who here has struggled with getting GPU reservations in the past? Okay, I know you're all experiencing this. And who here is concerned about the cost of running AI workloads? Come on, don't tell me you're not concerned about that. So today, we're going to show you how serverless GPUs are coming to the rescue with the recent release of the NVIDIA RTX 6000 Pro on Cloud Run and the launch of Gemma 4. We finally have the perfect match. Infrastructure simplicity meets massive hardware power. Our goal today is to show you that building a secure, scalable, and cost-effective enterprise AI application doesn't have to mean managing complex GPU clusters. It just means using Cloud Run. So let's build it. I'm Shir Meir Lador, head of AI engineering here at Google Cloud Developer Relations.
I'm Oded Shahar. I'm from the Cloud Run engineering team, and we have Ajay from Elastic here with us.
Awesome, and all of us together are going to show you, are going to take you through the full life cycle of an AI application, from a raw base model to a specialized fine-tuned expert running at scale. Imagine we are at Pet Life. This is our imaginary company for today. And at our company, everyone really loves pets, cats and dogs. But we run into this common problem where our internal Slack channel keeps on being flooded with images of cute rescue cats and dogs with the follow-up questions, what breed is this? And how do I actually feed them? And to solve this problem, we decided to build an internal tool for our company called Smart Pet Care. It identifies a pet breed from the photo and provides a tailored nutrition and health advice for that cute pet. Now, of course, we picked this very cute example for our talk today, but I want you all to look past the puppies and realize that this kind of pattern of multimodal classification and specialized reasoning, it's something that can be used in many other enterprise applications. For example, quality assurance in manufacturing or medical assistance in life science. So now that we understand what we want to build here at Pet Life, we need to talk about how to build it for an enterprise environment. As you all know, it's one thing to build a prototype. It's a completely other thing to build something that actually meets our organization standards. It needs to be easy to develop and accurate. For that, we will use a fine-tuned model to provide very high accuracy results. It must be secure. We will use IAP, Identity Aware Proxy, to make sure only our internal users have access. It must be compliant, so all of our data will sit in a single region. And most importantly, it needs to be cost-effective and scalable, leveraging Cloud Run, scale to 0. So we only pay for the GPUs where we're actually processing an image. This is our high-level design. You can see here at the top, the Next.js app is secured by IAP authentication only for our internal users. This connects to Gemma 4, which was recently launched and which is served via VLLM on Cloud Run GPU for fast multimodal inference. And to reach that specialist level accuracy that we mentioned, we're going to use Cloud Run jobs also on a GPU, to fine-tune the base model with our specialized data set. And finally, a GCS bucket will be used to store our fine-tuned model, allowing for rapid loading across the architecture.
I love to build apps. Do you all love to build apps? We're here to build stuff, right? So let's build the app together. We've broken this into 4 simple phases. First of all, we'll deploy Gemma 4 using VLLM on Cloud Run with GPU. Then we'll build our front-end app and deploy it on Cloud Run. We'll then fine-tune using Cloud Run job, the Gemma 4 model, and then we'll swap the model with VLLM again and see the result. For the first step, let me introduce you to Cloud Run serverless GPUs, where you can go from 0 to supercomputer within minutes. It's on demand, it's scaled to 0, first starting, pay by the second, and now with the new NVIDIA RTX 6000 PRO. With the phase 1 of our development, we'll deploy Gemma 4 31B on Cloud Run with GPUs. We'll use VLLM because it's incredibly fast for inference serving. Cloud Run serverless GPUs is the perfect fit for our application. Gemma 4 31B fits perfectly on the new RTX 6000 PRO GPU. It's easy to deploy. It has pre-installed drivers. It runs in our own container in the region that we choose. And remember Shir's GPU support group? The best part, no reservation required. It's on demand and scaled to 0. Now, let me show you how I do it on Cloud Run. So I prepared the command, the one command that I would use to deploy VLLM on Cloud Run. We pre-downloaded the model into a GCS bucket. Now, as you can see, on line 3, we use the VLLM latest container image. We'll then choose on line 4, we'll choose to use the NVIDIA RTX PRO 6000. And line 5 will mount the GCS bucket where we have the model weights. We'll then enable direct VPC, so we'll have fast networking into the GCS bucket. So we'll have fast cold start. And then we'll add a bunch of VLLM command line argument that we need, like run AI streamer. I'll now copy this command. And just paste it here. So as you can see, I can list the model from GCS. It's already there. And I'll pass the command. And now we're deploying Gemma 4 into Cloud Run. Just one simple command. While it's deploying, we'll now move into the front-end development. Move back to the slides, please. OK. With our backend deploying, we'll need a front-end. You probably know how to vibe code, so I'm not going to go through that. For our application, I chose Gemini CLI. I gave it all the requirements of everything we wanted, iterate on it until I was happy. And then, once we're ready to deploy, we just use the one simple command, just gcloud run deploy from source. And then, to secure our app, we'll be using the Cloud Run identity-aware proxy integration. This will ensure only users from inside our company have access to the application without trusting the vibe-coded application. Let me show you how it's done in the Cloud Run console. As you can see in the Cloud Run console, I have the Pet Analyzer UI already deployed. I have the URL to access it. And if I go to the Security tab, we have the option to enable identity-aware proxy. I can always go and edit the policy and decide who I want to give access. I just type in the email. For example, I can add Shir and gave her access.
I need my access.
Yes, Shir needs access to the application, but as you can see, Ajay, for example, is outside of our company, doesn't have any access to the application.
Sorry, Ajay.
Yeah. If we now, I can make it a little bit bigger. You can see, so this is the application. It's all vibe coded. And we add some settings here that look at all the Cloud Run services in our project. And we can already see here the VLLM backend that is deployed on Cloud Run. So we can select this one to use. And we can start a new analysis. And we can upload an image. So I choose this nice pet photo. Sorry, we have some Google policies here. Okay, oh, it's too big.
Let's see if it can recognize my cat.
Yes, this is Shir's cat, and we're gonna run the analysis. And it's gonna use Gemma 4. Gemma 4 is a multi-model, so it can recognize images out of the box. So, yay, it detected that this is a cat, and it gives us the key characteristic of it, the general temperature, care advice, what we need to feed it, dietary restrictions, and everything we need.
Yeah, there's one little problem. It did a great job recognizing it's a cat, but it's actually not a European shorter cat. It's a different kind of cat.
Okay, so now Shir, now tell us how we solve this problem using fine-tuning.
Okay, so let's go back to our slides. In the world of powerful models like Gemini, why would one even consider fine-tuning? Well, we talked about it, we thought about it a lot, and there are three main reasons usually people go to fine-tuning. One is in case you need very, very high specialization. Like in our case, we have 37 different breeds of cats and dogs we need to identify with very high accuracy to make sure they get the right snack, right? So fine-tuning in this case is the necessary bridge that transforms the general broad reasoner to a high accuracy expert. The second reason is around security, control, and sovereignty. When you have to host your own data and you are not allowed to send it to external APIs, then using an open custom model, hosting it on your own environment is probably your best bet. And the third and most interesting one, to my opinion, is cost efficiency. First of all, I don't know if you're all aware, but Gemma 4 was just launched, and it is our most capable model family that can run on a single GPU or TPU. So this is one point about cost efficiency. And in addition, when you are hosting your own model, instead of sending it to an external API, you're only paying for the hosting. You're not paying on all the tokens you're sending to the model, like you do when you do with the Gemini or Claude or any other model. And with Cloud Run, when you don't send anything to the model, it actually scales to 0, so you don't pay. That's pretty incredible. And one more thing I wanted you to think about is last year, NVIDIA published this paper that says that small language models are the future of agentic AI. It is because they are now at this stage, especially now with Gemma 4, they are at the point where they are sufficiently powerful to invoke most of the agentic invocation, to perform most of the agentic invocations. And they are a lot more economical. So I hope you have some food for thought about that. Definitely you do if you are here. And now that we establish when do we need fine-tuning and why, let's talk about how we are doing it with Cloud Run jobs. So you probably remember our support group from the beginning when we talked about our challenges with reserving GPUs and managing clusters. What is really nice about Cloud Run jobs is that we can actually fine-tune models without managing clusters or without reserving GPUs. in the very similar manner, just by running a few commands, like Oded showed before. And with the new powerful GPU, the RTX 6000 Pro, yeah, we use it also here for fine-tuning, you can now run significant training workloads more efficiently in a serverless manner. You see, we fine-tuned here Gemma 4 with 31 billion parameters, and we could actually go bigger than that with the memory this GPU has. So how does the fine-tuning look like? Like any other fine-tuning, we load the model from Hugging Face. And one really good efficiency hack for you all that you should remember is that it's a lot more efficient to go ahead and download the model first to a cloud bucket and then have the fine-tuning job read it from the cloud bucket and not from Hugging Face. Because it's a huge model, it takes a lot of time to run. Think about that the next time you do the fine-tuning. So we have the fine-tuning job running. It takes the model from the cloud bucket after we put it there in advance. Then we run the fine-tuning using Cloud Run job with the GPU. In our case, we use parameter-efficient fine-tuning, LoRa. And this means we only update a small subset of the weights of the model that we inject to the model layers, which allows us to fine-tune a lot more efficiently, requiring less memory, enabling us to use much smaller GPU memory. Then we store the fine-tuned model in the cloud bucket. And in terms of the results, so for Gemma 4, we were able to get from 89% to 94% accuracy in just 4 hours, which is nice. I mean, it's not crazy, but the reason is that Gemma 4 is really, really strong. I wanted to tell you that when we did this with Gemma 3, before Gemma 4 was released, the baseline accuracy was actually 76%, and with the fine-tuning, we were also able to reach 94% accuracy. So just because Gemma 4 is really strong, so shout out to that team. Okay, so now after we have the fine-tuned model stored in our bucket, let's go back and see how the entire application comes together with this high-level, high-accuracy model, which is, by the way, state-of-the-art for this data set.
Okay, so now that we have the fine-tuned model weights in GCS, we can deploy the specialist model into Cloud Run. So all we need to do, same as before, just a single command, we can deploy the model. It's exactly the same command as we used before. We just change one parameter to point VLLM to the new model. Okay, switch to the demo. Now I can go back to our vibe-coded app. And we already deployed the model before the session, and it's running. So I'm going to keep both of those. And we can try new analysis. Now we choose the fine-tuned model, give it a nice name. I'm going to choose Shir's cat again.
Let's see if it gets this right this time. This 5% helped.
And voila.
Yeah.
It's an Egyptian Mao. And now we can make sure we give it the right snack. Back to the slides. Now that we finished building our Pet Life Incorporated app, we can see that we match all the requirements we wanted from the model. It was fast and easy to deploy. It is secure with IAP. Only our internal users can access it. It's compliant because we only chose one region that all of our data exists, and all the data exists within the containers that we own. It's cost-effective because at night when we go to sleep, it just scales to 0 and we don't pay for the GPUs. And it's scalable. With Cloud Run auto-scaling, it will scale more as we get more traffic. But to talk more about scalability, we have Ajay from Elastic that will tell us how they scale their GPU workloads on Cloud Run.
Thanks, Arun. Hi, folks. I'm Ajay. I'm the GM for platforms and core services at Elastic. And I'm here to talk about how we use Cloud Run to serve and host our cutting-edge embedding models, processing almost 1 trillion tokens a month, so slightly more than the CAT service. So much like Google, Elastic has spent the last decade being synonymous with search. Search and relevance play a key part in our lives, from finding shoes in your favorite e-commerce site to finding the nearest Uber. In the age of AI, the precision of search to find exactly what you need is more than just a box on your screen. It's become sort of the foundation of intelligent data access. And many of you, teams are under immense pressure to find sort of accurate and efficient ways to put petabytes of unstructured data to work. And managing the infrastructure to do that comes with cost and friction that few companies can afford. So Elastic, as the search AI company, integrates its expertise in search technologies with AI to harness that sort of exponential growth of underutilized data to answers and outcomes. The products that Elastic offers span from observability, where we're taking millions of signals around logs, metrics, traces to help you find and determine incidents, to security events, managing trillions of events coming in to find threats before they become incidents, as well as powering conventional search stacks, like acting as a data store for finding your e-commerce backends and so on and so forth. One of the areas that we have really been pushing hard on, or where we've seen a lot of traction recently, is being the backend for agentic and AI applications. And this is not by accident. Over the years, we have invested significant amount of work into improving our speed, scale, and relevance for the kind of workloads that AI excels at, from vector representation to quantization of how we store those pieces of data, to having 95% more memory efficient ways of representing vectors, to techniques called ACON for about retrieval and improving the velocity that you see with it. We have been making significant impact and effort to say, Elastic is your choice for building AI and agentic applications at the back. We are the most downloaded vector database, in fact, as it stands right now. So key to that strength is the power of relevance and retrieval, which I think sometimes gets underappreciated in the agentic era. Everyone focuses on the model, right? The LLM you're using, but whatever LLM you're using, how many other parameters, whatever benchmarks it scores, the model's only good as the data you feed in, right? Even a 70 billion model is going to produce garbage if you give it garbage. Sometimes it'll identify the wrong cat, and even though the accuracy is kind of great over there. So that retrieval layer has two components that matter a lot. So first is think about embeddings that convert the content, be it text, images, code, into vectors. Vectors are numerical representations of your data that capture the semantic meaning. So that's something that will allow you to say, a document about cardiac events and heart attack are actually the same thing, even though the words are not exactly the same, even though the tokens are not exactly the same. Second is the concept of a re-ranker, right? So re-rankers work on top of that. You give it the query with the collection of vectors that you just retrieved, and it scores sort of deep cross-attention on top of that and gives you a better way to correlate what the actual relevant signal out of that is. So it's a little bit more computational intensive than a simple sort of similarity match, but it gives you a lot more relevance over there. So as Elastic, over the years where we have built so much deep capacity on indexing, retrieval, quantization, cost optimization of storage footprint, one of the areas we also saw ourselves saying we have to get better at these applications build is re-ranking and retrieval. And that led us to acquiring this company, Gina.ai, which is one of the world leaders in building open source embedding and re-ranking models. We got them over in October 2025. They currently have about 17 models that are out in production. Their complexities is that they rank in the top 5 of most benchmarks that are out there. Their re-ranker model currently has about 35,000 tokens in terms of the capacity that it can put out there. And for us, that also brought in a new surface area of us running on top of Google, which was the Cloud Run stack, right? So Gina had built its stack or serving platform using Cloud Run. Elastic uses various forms of Google infrastructure in its various cloud offerings, but this was our new interaction when it came over there. So Gina itself isn't a monolithic offering, right? So for each of the things we talked about, just when you talk about re-ranking and embeddings, there are 17 plus variants. And those variants are because of size. It could be because of the task that they're doing, depending on image or video or text. Re-rankers have versions, so re-ranker V1, V2, V3, V4. There are specific models like Colbert that represent certain quantization behaviors. There are vision language models. So each one has very, very different traffic patterns, resource needs, memory footprint, latency requirements, right? When you're running a re-ranker model that does post-processing query, when I'm trying to give you suggested results at the bottom of an e-com site, is very different than if you're looking to find the nearest location of your coffee shop to go and pull that in. That needs to be much more instantaneous, very different profiles that go on there. When Gina started building early, the early instinct was to build shared GPU pools, as many of us start. GPUs are expensive, big boxes, put a bunch of them in a room, stuff them. They literally had a bunch of them in a room racked up that they were getting going from. So there's a nice little picture I wish I had access to that I could put up here. The problem is shared pools creates two compounding failure modes, right? First, right sizing. All these models have crazy different requirements, different memory needs, different traffic spikes. You're constantly tuning allocation. Every change carries a blast radius risk. One model takes down the other because the GPU is saturated. Conventional infrastructure packing problems. Second is idle cost, right? So you have specialized models like Colbert that were used very rarely, but when they use pretty aggressively. So, thousands of requests per second, but the rest of the 11, 12 hours or 14 hours during the day, they are idle. So having dedicated GPU pools sitting around managing that pool of machines is complicated. And when you're running at a pace of iterating and putting out new models, you now add a capacity decision to each one of them. You're sitting and figuring out how many machines do I need for this collection of boxes to run together, how many models do I need, et cetera. So none of those were set up well for Gina or any of us to kind of work through that. So fleet complexity, GPU cost, ops overhead, all of which made it a tailor-made solve to go and explore Cloud Run as the underlying solution for going and doing so. The big architectural solution that shifted sort of from a mental model perspective was treating GPU as fungible compute. Right? The moment you stop treating GPUs as a specialized single box or anything of that sort and say GPU is a compute pool like anything else, that changes the mental model at which we go through. And concretely, what that translated to was, one model, one pool of GPUs, ideally with a scale to 0. So what did that actually look like in a Cloud Run setup? So first, there's a straightforward entry port, which is the API gateway, which is also running as a standard Cloud Run service. So no GPUs or anything, just a classic app that is deployed onto there. This accesses kind of the incoming gateway. So it has IP-based rate limiting. I think we have about 10,000 requests per 60 seconds. But beyond that, it throttles it. It does things like authentication with different levels of tiering. Each tier has a different request per minute, token per minute throttle, concurrency limits, config-driven routing, all of that built into the app itself, depending on the nature of models that we're going for. It also handles routing to the different downstream models, which are sitting there, as well as handling async usage reporting for billing. So all of this, that by itself is a pretty reasonably complex app that is running on Cloud Run that in today's storytelling just sounds like cool. It's done, it's up and running. Now, behind each gateway is each variant running its own Cloud Run service with a dedicated L4 GPU, each configured with min instances equal to 0, right? And below that, you'll see we have kind of a regional deployment model. Gina itself continues to have a standalone public presence. So there's a public.gina.ai that handles that particular traffic that runs in US Central 1. And then all our internal embedding, so data that is stored within Elastic that goes through Gina models for embedding or re-embedding or re-ranking comes through another region which sits in US East 4. And even there, we have actually partitioned it out into a traffic that is more latency sensitive, where you have to kind of have a quick response, so sparse requests but rapid response needed, as well as heavy-duty batch inference-based requests that sit over there. So why I'm calling all of these out is all of these combinatorials, the model plus these different traffic patterns, each runs as an individual Cloud Run service. And the routing for that all is handled by that incoming API gateway over there. A few interesting things that I want to call out as optimizations, as real-life examples for you all to do. First, you will notice that we also ended up using VLLM as our runtime environment for hosting the model. And conventionally, you think of VLLM as working only for LLMs. Like, why would you use it for any other models over there? So turns out the batching behavior that VLLMs have lend themselves really, really well to any other kind of models as well, especially for embedding models where you're transferring a bunch of finite data, especially vectors, back and forth over there. It allows us to saturate the GPU far more effectively than you would if you were not using that enable model. So one piece of advice for all of you is no matter what model you're using, flip around that particular element of sort of enforce eager equals true, because it allows you to saturate the GPU more and get a more efficient footprint. The second one I'll actually, that is VLM continuous patching. Enforce eager equals true gave us another one. So this was a cold start problem that we ran into. The CUDA footprint of the model that we were deploying when it was parsing into memory was taking anywhere between 4 to 25 minutes. Now, I know we all don't like cold starts, but no one likes a 25-minute cold start, right? And turns out, if just by flipping that one particular one of saying enforce eager equal to true, it did not load it into memory. Cold start drops to seconds. It drops the throughput a little bit. I think we saw kind of single-digit drop in the throughput that a per model service could use. But for our embedding models, it didn't make a big difference. So it was interesting that just by fiddling around with the settings that are available on the GPU itself, we made a huge difference to how the cold start serving itself was happening. And then another one is sort of the point about the LoRa checkpoints that Shir was referring to as well. So LoRa, as she described, are ways to add variance to the model, like with smaller embeddings that expand the behavior or change the behavior of the model itself. And when we're running variance for us, it makes a difference, right? Like you put a single model which has got 60 billion parameters, you can now add these adapters, quote unquote, that allow it, with a few million model parameters, get a different behavior for it. Initially, when we did it, we were trying to dynamically load it. So we had the base model load, and then we would dynamically swap out the adapters as it was going through. Turns out that creates memory variance. Latency was getting pretty horrendous. If there was a cold start of the model loading, it was kind of creating an extra load on that particular one. So we tried to be too smart on that one and decided, no, the simple answer is the better one, which is just build the container separately with each of the adapters, and we ended up just creating more Cloud Run services. And the decision for us was actually easy because of the min instance behavior that we had, right? Because each service was individually scaling down to 0, splitting 1 into 4 was just a question of adding more to the routing stack that we had over there. So with me so far, like all the variants of the models, each running in a different Cloud Run stack, each sort of fine-tuned in different ways, both in the build story as well as in the inference story. And the interesting thing is there are optimizations both on the model building part as well as in the GPU part, but it actually was super easy on Cloud Run that there wasn't an abstraction that made it hard for us to reach into the GPU or make changes or anything of that particular sort. And so what did we end up with? So we serve about billions of inference requests a month. I think the last clock was about like 1.2, 1.3. We have peaked out at about 800,000 tokens a second, so about close to 1 trillion tokens a month. So it's a pretty solid, heavy-duty production workload running on serving these with sub-second, tens of milliseconds workload inference during the hot path. Each model has its own P99 latency SLI, error rate SLI. We did end up using PagerDuty for monitoring it, not the Google services, but the integration was straightforward even within Cloud Run because of the ecosystem support that we had over there. And the core value pop over there as much, right? The number of services that we're running, each of them has its own isolation, each of us has its own scaling behavior, each of them comes with scale to 0, so there's 0 fleet management that comes in over there. And it allows us to keep sort of that open by default behavior because we're able to iterate a lot more faster in getting the pieces out. So what's my note to all of you, right? First, serverless GPUs is a real thing, right? We're using it in production. It's a multi-region deployment. You can integrate it with any of your production operational stacks that are coming in there. There's a whole bunch of configuration options that can really get you to fine-tune what you need to kind of get it out there. And cold starts, honestly, we're serving large models. We're on the hot path. It's not a real problem, right? Like we're looking at maybe a couple of seconds once in a while affecting your P99, but serverless and cold starts, it's 2019. So leave it aside. Don't bother about it. I'll strongly encourage you to think about isolation strongly. I think Cloud Run and serverless in general lends itself to really thinking about one model of your scale and cost behaviors running as a separate unit. Failure modes is good. Deployment models, it's simpler to deploy. We use the Google Cloud Deploy capabilities for pushing the models out. The integration makes it super simple for us to go and do so. Scale to zero actually gives, the diversity helps us. So even though individual services have like spiky behaviors on that, when you take the collective running across the whole GPU pools over there, we actually get a much more compacted, cost-efficient pool of GPU use as if I look at the individual ones more than anything else. So if you're using Cloud Run in different ways, consider a more diverse workload rather than running each one that goes over there. And as with all things, good hygiene applies. Push as much things into build config as possible. Please don't make changes dynamically onto a model that is already dynamic in nature, sitting on GPUs, which is a dynamic piece of infrastructure. Try to put everything on build config. Keep your invoke path clean. Always a good idea. So yeah, I'll finish with that thought, which is, relevance has always been Elastic's core differentiator for a decade. And Gina gave us world-class embedding models that made it a native platform capabilities, and Cloud Run gave us the infrastructure to run at a scale with a dedicated platform managing GPU clusters. And I feel like together it allows us to ship model variants a lot faster, iterate much more faster to improve the relevance capabilities that we have for customers. And I'll leave you with that thought that, for anyone who's going to try this out in production, the playbook exists, right? We have gone through the path. Open-weight models on serverless GPUs is a real thing. And get onto it. And happy to answer questions after this. I'll pass this back to Shir. Thanks.
Okay. So before we say goodbye, we wanted to give you a few more opportunities to continue your learning journey. So first, tomorrow morning, we have a deep dive with Oded and myself, where we are happy to, hear your questions and thoughts about these topics. So please join us. It's 8:30 tomorrow morning. There's also a meetup tomorrow at 9:30 for Cloud Run developers, and also a few other interesting sessions that might interest you tomorrow. So feel free to snap a photo of this. And most importantly, if you are interested in trying for yourself, and we really recommend you do, we want to give you a mission. Go to the Cloud Run console and deploy Gemma 4 with just one command, like you've seen Oded do today. And if you want to see how to do more of the advanced things we did today, so here are the QR codes to all the code. First, for fine-tuning Gemma 4 with the RTX 6000 Pro GPU. In general, fine-tuning with jobs. There's a full lab here that goes step by step. And also another lab to show you how to run inference on Cloud Run with the RTX 6000 Pro GPU. So snap a photo, take the barcodes. All the code is there for you to try. And we would very much appreciate your feedback about this talk. If you have thoughts about what we should have talked about more and any other thought that you have, we would love to hear. Thank you, everyone.
All right, thank you.
Bye-bye.